Good afternoon. I'm Hugh Dyer, an Associate Director in RSK's Geosciences business. Welcome to the final edition of our 2024 series of Down to Earth webinars. These we cover a broad range of subjects and are available afterwards on our YouTube channel alongside our previous talks. Our talk today will be given by Dr. Charlotte Usher from our geophysics team, providing a guide to the use of geophysics within the assessment of structures. But firstly, a brief note on housekeeping during the talk. All attendees' microphones are automatically muted to the webinar. During the presentation, you can post questions online and there will be a Q&A session at the end of the presentation. We'll answer as many questions as possible. Those that can't be answered due to time constraints will be answered after the webinar. And shortly after the webinar, you'll receive a link to a short survey. If you can take a few minutes to provide feedback so that we can improve our future webinars and make sure we've got some good talks in for the 2025 series. Now, please let me introduce our speaker today. Dr. Charlotte Usher is a chartered geologist and principal geophysicist. Charlotte joined RSK following her PhD and has been part of the team for nearly 10 years now. Charlotte is technical lead for geophysics within RSK and is actively involved in research and development, as well as working on large-scale commercial projects. Charlotte was the lead author for the new Syria guidance C812, and Charlotte aims to make communication of geophysics more accessible to increase engagement and use as an alternative to or to help target intrusive investigations. So I'll hand over now to Charlotte to give us a guide to the use of geophysics for investigation of structures.
Thanks very much, Hugh. Okay, right. Okay. Yes, welcome everybody. This slide shows what I'm planning on going through today. First, I'll have a quick overview of something that I have talked about in previous Down to Earths. So why are we using geophysics? What are the benefits of this mystical survey type? I'm then going to present a series of case studies where we've successfully used geophysics on structures with quite a significant focus on the application of GPR, and I'll explain why that is in a moment. I've also got a couple of examples to show you that aren't GPR, just for a bit of variety. And then we'll have a quick summary before we cut to some questions. So, on to the first section. Why should we use geophysics? So, why should I use geophysics? It's a common question that we get asked. As has been discussed in previous webinars, there are a number of advantages to using geophysics within your investigation. So the first two, it is non-intrusive, it's non-destructive. So lots of geophysical surveys, they don't break the surface. They leave little to no evidence of them having taken place, which can be really important if you're working on key historical landmarks or listed buildings where we don't want to do any damage to the structure. The information is spatially continuous, so we can fill in any missing gaps between intrusive samples, which overall will produce a more detailed model. It's safe to use in the fact that most geophysical equipment is light enough to be hand carried and operated, so it doesn't affect any integrity or stability of a material, which is really important when you're working on structures that are potentially damaged or could further damage. They're rapid, so there's certain surveys that we can use that can cover large areas quite quickly, which is good where we've got time constraints where we're trying to identify if there's any further damage to a structure. They're cost effective when they're used effectively, so they allow for this quick look at an area, which you can then use to then further target investigations rather than just digging blindly in the ground. And also, as I mentioned earlier, you can integrate all of this information into a model. So when you use your geophysics data alongside other data, such as built drawings, intrusive samples or monitoring, you can then use this to produce your robust model of your structure or study area, and that can then be included as part of the design phase, which can then help to determine the next steps that you want to use in your project. But as with any surveys, there's also limitations that you need to consider. So while we can, in some cases, achieve quite a reasonable survey depth, this is usually at the expense of a reduction in the detail or the resolution of the survey. This will vary depending on the survey type and how you set it up. So there's a number of factors we can control that will help us get the most out of our data. Geophysics surveys also require a contrast between materials, so you need to have enough of a difference that's measurable for your technique in order to detect any boundaries. So this doesn't mean that that's going to be true for all geophysics techniques. So you may have a property contrast in one that doesn't necessarily present in another. So for example, you may have an acoustic difference when you don't have an electromagnetic one. It depends on what material the structure is made from. Some techniques can take a lot of time to collect. So they're better used as targeted techniques, such as microgravity. And some may also require more complicated processing steps, which means that the answers are not going to be presented then and there on site. Some surveys can be limited when there's interfering noise, which is any sort of unwanted signal that comes in. It's non-interpretable. It can actually mask actual features, unfortunately. And steps can sometimes be taken at the design phase to help reduce the impact of that. Many surveys need physical contact with a surface in order to function correctly, which can be a problem if you've got an intricate building facade, for example, which can restrict your access. Again, this is all about effective survey design to maximize your coverage as much as possible and get the most out of your survey. There's certain ground materials that can reduce the penetration depth of the signal, or there are structural elements that can also reduce that through scattering of energy, such as rubble-filled cores or high conductivity clays. So having as much information about how a structure is constructed or what is going on in the ground will help us with designing our survey and then get the most out of it. And finally, your ground response can be really variable, or material response. Any interpretations that are made are generally based on the experiences of the person doing the interpretation, but in a similar environment or site condition. So like any intrusive investigation, there's going to be potentially a bit of subjective bias, and that will be based on the competence of the engineer. There's also potentially multiple solutions that may be possible, so multiple causes of an anomaly, and until we get further information to validate that information, just to prove what has caused it, it's going to be, to a degree, an estimation. So that's why it's really important to use the geophysics alongside other data sources where that's possible. So this is relevant for any geophysical investigation, including structural ones. So when geophysics is brought in early and it's planned well and can be used alongside other data, it can produce a robust model that can help you target any remediation or later stages of work. And when it's used effectively, it can save projects money. It can avoid your additional costs from these unknown issues that you didn't necessarily know about. It can require fewer samples, and then it can also cause less damage to the structure that you're working on, which is sometimes a key thing here. Structural assessment is commonly used to look for flaws within a structure. Quite a lot of the time, these flaws are quite small in scale. So we tend to choose techniques that have a high resolution that can show us this fine detail. And a common technique we would use for this is high frequency ground penetrating radar. So generally we're looking in the range of 900 megahertz to 2.6 gigahertz. GPR is a really versatile technique. It has so many different frequencies and antenna combinations we can use. It can sample both in cross section, so showing you a slice through the material, highlighting changes with depth, but you can also use it to map changes across the surface. Because of this, we commonly use it for our structural assessments. And that's why a lot of the case studies I'm going to present now use GPR in different ways. So hopefully this will highlight to you the number of different ways we can use GPR within structural surveys and what things we can visualize from this. So the first case study I'm going to present is Bramshill Mansion. As I understand, this was a former National Police College. It's one of the largest, most important Jacobean mansions in England, but it was in a really poor state of repair. It needed millions of pounds worth of repairs. The front facade had previously had some remedial works to hold up the stonework, but these were starting to rust and spoil the stonework off. We used GPR to try and find this embedded metalwork, which could be used to then help target the remedial works. Access was tricky. We had to use a mobile elevated working platform, which you can see in the bottom right of the image. And as is also the issue for listed buildings, there's lots of areas of intricate stonework, and this can limit the GPR survey locations. We used a high frequency radar, two frequencies of high frequency radar in order to get this detail that we needed of the metalwork, as it's usually quite small in scale. As I mentioned earlier, we need access, we need flat access of the actual radar antenna to a surface. So this restricted us to only the flat sections where we could move the instrument with a good constant contact with the surface. And that's then further limited by the size of the GPR instrument itself. You can see an image in the bottom of this slide is the 900 megahertz GPR. That size is fixed, we can't change that, and that size needs to be considered during the design. This image on the right with the arrows gives an example of the sort of number of survey lines that we were able to achieve in this instance. So these tended to be limited to the flatter sections of walls, along pillars, and above and below windows. Luckily, the data we got in these limited sections was quite good. The data shown in E11 in the image in the center, that was recorded along a survey line that was moved vertically to the left of the main entrance door. You can see there are some reflections from interbedded metal objects shown by the bright high amplitude features labeled with the number 1. And you can also see the back of the slab, which is shown by the constant reflection labeled with the 2. This, the depth that's shown on the side of any of these ground penetrating radar depth slices, cross sections, generally these will have either been approximated based on a known velocity for the material that we understand we're surveying over, or through calibration from known depths to metalwork. The data in E7, that's been recorded as one of the vertical lines down the left of the ground floor window. And you've got further features in here with a hyperbolic feature on the left labeled 3. That's the kind of arch shape. That suggests another bit of metalwork within the structure. And there's another bright feature highlighted with the number 4 and the circle. That's a suggestion that that could be evidence of delamination or further defects within the structure. So those sort of features have been highlighted as well. And as you can see from this image, there were a number of different features that we were able to highlight within this survey. And this allowed us to provide that information to the client, who could then do further assessment and then repairs on the structure. The next case study looks at a factory building in Hythe, where we were surveying the floor of the building. This is another listed building of historic significance. They built seaplanes here and flying boat hulls for the Admiralty during the Great War. In this case, we were looking again for metalwork. So we were looking for the position of any reinforcement within the floor slab, as well as details of the slab itself. Again, we used a couple of different frequencies of radar here. We've got a higher frequency, the 1.5 gigahertz, to get the detail of the metalwork, and the lower frequency, the 400 megahertz, to sample to a greater depth. The radar data that's presented on the left here is an example of the high frequency data shown in cross section, and we're able to identify a number of structural features from this. So you've got your smaller reinforcement bars present in these nice evenly spaced hyperbolic, like arch shape. They're quite narrow because these represent quite small metal beams, but we can also see there's wider features which represent the wider primary beams. These are features that are larger in size because they represent a larger item in the ground. and they have a slightly flatter shape within the radargram that tells us that. We can also look at how these features look across the whole survey area. So where the radar data is plotted in plan view, we can take a slice across a constant depth. This is called a depth slice. It's a good way to see how features relate to each other across the site, and how that changes with depth potentially. And you can see we're able to excuse me, identify areas where there was actually a apparent absence of beams or joists in this area of the site in the left. As always, we would caution that the absence of a target within geophysics doesn't necessarily mean there's nothing present there. It might be that in shallower depths there are features that have reflected most of that signal energy back to the surface already, which I'll highlight in a case study later, and that will potentially mask any features below that. You can also see in this image C, the bottom radar data, we were able to identify there were certain areas where the rebar was sagging across the slab. We also had 3 ground cores sampled at this site, and from this we were able to verify the thickness of the slab at each of these locations, and this could then be used to calibrate our GPR depths across the site. So overall, this is a more accurate way to calculate the depth of any features. We can then use that information to produce what is shown here, which is a contour plot of the thickness of the concrete slab across the whole floor area. And you can see within this areas that are then thicker or thinner, and hopefully that can be used to help target remediation of that. Using a similar method, we were able to map out the cover depth of the metal reinforcement within that slab, which was really important to highlight any areas that were deeper in the slab, such as down the bottom end of the site, areas where there was significant variation in the depth, such as on the left, where we have the sagging detected. There's an 80 millimeter variation present in the rebar depth, and this is thought to be due to the presence of the support beams where it's shallower. And this is again something we can use to highlight areas that are in need of repair or replacement, or even in certain cases like this, and areas where there is an apparent lack of reinforcement present at all. It's not often we get to search for the unknown, which was the case at this next case study. It was less important for us to have very fine detail in this survey. We were looking for archaeological features that were potentially at a more significant depth. So we opted to use the lower frequency 400 megahertz GPR. This is going to see down to about 2 to 2.5 meters below the surface in general, depending on the conditions. And this is the same sort of frequency we typically use for utility surveys. There were several anomalies of interest that we found, some areas of anomalous reflections, some of which were linear in nature, so that meant that they occurred in a similar sort of place within lines that were running next to each other. Most interestingly, there were some large hyperbolic features, which you can see in the bottom right radargram. These were observed beneath the main steps, and they seemed to indicate a vaulted basement structure. And we were able to take these anomalies that we found and map them out over the steps and courtyard area to be able to demonstrate what we'd found at the site. We ended up, so we produced this map. This is on top of the actual structural drawing, and we highlighted several narrow linear features, as I said, shown by these green lines, which are potentially metalwork or utilities within the courtyard area. And also in the center here, we've got these blue rectangles. These are highlighting the position of these possible vaulted basements. Sorry. And they actually managed to investigate there, and it was great to see we'd been correct. Blenheim Palace were also really happy, because while these had been present under the main steps, they had been unaware of their existence up until this point. A lot of these surveys so far have been kind of focused around trying to find voids or features that shouldn't exist or that the client didn't know about. And in this next case study, there's a known void that the client wanted mapping, and that's chimney flues. This is high frequency GPR data with the 1.5 gigahertz, and we're able to see the reflection shown by the number 1 of the front of the flue, which is the edge of the void, the brick to air interface, and then also another reflection from the back of the flue, which gives you a kind of indication of the size of the void space that is present. You can also see, as I mentioned earlier, that in reflection 2, which is possibly the back of the wall behind the flue, there's actually a gap in the reflector in the center, which has been caused by all of the energy reflecting off the flue void space. And so there's not enough energy for you to be able to detect the back of wall reflection behind that point. So that's been masked by that feature that's a bit shallower. These void spaces can also be mapped using the same spatial slicing method that I showed in the previous example. So at a fixed depth into the wall, we can map out these flues, and in some cases you can even see fireplaces at the bottom of the flue, which is quite nice if you're looking at larger spaces. These can then be interpreted to highlight where the flues are going within the structure. This approach is also really good for detecting if there's any potential blockages within the flue network as well. So either from collapse or things blocking the way, as I say, such as men in red suits who I hear get stuck. At certain times of the year. The brick to air contrast is one of the strongest concepts in GPR. So it's going to produce a really bright reflection. If there's any material stuck in what should otherwise be a hole, this would then present as a weaker contrast, so a fainter reflection in the GPR, although this will obviously depend on the extent of the blockage or the damage. Using similar techniques, we can also use GPR in tunnels, so where we scan the tunnel walls to look for potential voiding in the walls or delamination within the materials, as we're doing in the case study I'm showing here. So again, we're effectively looking for what are bright spots within the GPR data, and these can then be highlighted to then target any intrusive investigations further. In this case study, there were some floor slabs that were coming loose. It was believed that the grouting adhesive beneath the floor tiles had not been sufficiently applied. So we completed a 2.6 gigahertz, so really high frequency GPR survey to get a very high level of detail over the floor slabs. And we were looking for, again, voids, so gaps, which appear as strong reflections. And we mapped this out as depth slices, and we can see these strong reflections of the voids present in the areas around the grout. So once the slab was removed in the image on the left, you can see that this matches pretty well with the results that we got from the GPR data. Hopefully most of you will remember the Toddbrook Reservoir disaster back in 2019. There was a series of unfortunate events. Series of unfortunate events that included high rainfall, much like we had over the last weekend, which caused an overtopping of the dam structure and caused an overall failure of the spillway structure. And this involved the evacuation of 1,500 people from the downstream town of Whaley-Bridge in Derbyshire. The investigation that followed this incident involved RSK being sent out to investigate the spillway construction. We used a range of GPR frequencies to assess the internal metalwork, as well as the potential construction changes that may indicate voiding or any disturbance within the structure. We were able to map out variations within the dam, such as the cover depth of the rebar reinforcement, which is shown here on the left. In the radar data that's shown on the right, you can see there's a variable depth to the reinforcement, which is this kind of blue layer right at the top, labeled with the number 2. This kind of represents an area that's the area that's labeled with 3 down the bottom. This represents a possible change in ground conditions below the slab, which potentially indicates an increase in the voiding or the saturation beneath the actual structure. Following the examination of this spillway, as a result, we were involved with the following Environment Agency guidance. So this involves the examination of spillways. It discusses the techniques that are generally used to investigate vulnerabilities in concrete, many of which would potentially be relevant for other concrete structures. So it might be worth a read in general. Now, hopefully this is a landmark that most people will recognise. Now, while this is still discussing the use of GPR on a structure, it's a slightly different application to some of the other studies I've been talking about. In this case, we were looking for areas of moisture within the timber decking, which is along the road section of the bridge. So we needed a really high level of detail. So again, we selected a really high frequency of radar. As you can see, we have some of these arch-shaped hyperbolic reflections, which are present in the structure. They look larger within this data set because we're only looking down about 40 centimeters within this cross-section. And the layer that we're interested in is this flatter layer above that, which is the top section of the wood. And we know that there is a relationship between how fast the energy travels down to the bottom of that wood and back, so the travel time, and the moisture content. So the wetter the wood is, the longer it takes for that journey to happen, because the presence of moisture will reduce the speed of that energy, but it will also reduce the signal strength potentially. So we can also use the size of that reflection to help with our assessment. In this case, we also had some core samples taken, which again helps us to calibrate and validate our results. These samples were taken to a laboratory and were oven dried to measure the change in weight and therefore the percentage of water. Obviously, as these were lab tested and not in situ, there will be some difference to what's measured in the lab, just based on loss in transit and stuff like that, but it'll only be small. And overall, you can see when we compare these lab values, which are in the kind of red color in this graph below, to what we calculated from the GPR, generally, they largely match really well, which was really made us really happy. And you can see we've been able to then map this out as a kind of contour plot across the whole bridge area to highlight areas that are potentially wetter than others. So obviously I've shown a lot of examples of GPR, which, as I said, it's a very versatile tool, but there are other techniques we can use, particularly if we're looking at changes in structures within the ground or at greater depths. This first example is in Welwyn Garden City. It's a former industrial estate. It used to look like this. This was the original building on the site. When the site was bought out, the owners wanted to confirm that the building structures, which had been flattened to ground level, as you can see here, had indeed been removed from the ground, as had been alleged by the previous owner. So in this case, we were commissioned to do a electromagnetic conductivity mapping survey, so using EM, which showed us this. The warm colours, so the reds, these show us places where there are conductive features. So in this case, we have buried concrete foundations, metal tank up in the top right, and some pipes running across the site. And there's also a potential pollution plume that fortunately just turned out to be raw water. But as you can see, these features are still very much in situ, and the geophysics helped us get a more complete view of the subsurface. On this final case study, we've got a school site. They'd experienced a collapse in the playground. It had produced quite a substantial hole, as you can see on the right on this image at the bottom. Microgravity is a really good technique for looking for voids or areas of low density in the ground. It is a bit more time consuming, which is why it tends to be a second phase technique. But in this case, we were able to complete a gravity survey over the whole playground of the school. We were able to map out the area, and this showed that there were 4 areas that are highlighted blue in this top corner. So these show areas of possibly relatively low density. These were then targeted with some dynamic probing, and you can see from the plot in the center here that at about 3.5 meters depth, the rods fell through into the ground, proving that there was a void present in that location. These sort of voids, they can be common in areas where there's things like limestone bedrock, for example. And in this case, they were able to easily target and then grout up the holes, which then made the playground safe so that the kids could return to school. So I've covered a number of examples today. I've discussed how we can use geophysics to find something, whether that's under the ground or within a building facade, doesn't really matter. We can usually find out a lot of different information about things that are concealed beneath a surface. Any information that is provided that can be used to help that geophysical survey will only make that survey better. And then in combination with the geophysics and any other data, we can use that information to then help target further investigations and help remediate any damage if necessary. And overall, this reduces the risk for people on site. Thank you for listening.
Thank you, Charlotte, for that very interesting, very excellent talk. We've got a few questions that have come in through the portal, so if you're happy, we'll kick off with some questions. Someone asked, can you tell the difference between metalwork and cables in the brickwork, and also can you recognize voids? And then can you recognize the difference between voids and pipework or ducts?
Right, lots of different things there. In using just GPR, generally a lot of these things, such as metalwork or voids, would appear as bright reflections, and generally we would make an assessment on the shape of those features to determine what we felt could possibly be the cause, as well as you'll have noticed there was blue and red within a lot of our radargrams. That indicates positive and negative responses, and that will also be indicative of the material that is potentially made of. So there's a lot of different things we can use to try and determine what it's been made of and what sort of object it might be. So for example, our pipes and our cables, they tend to be more of the hyperbolic shape because they tend to be a point source, and how wide that hyperbola is will depend on how wide the pipe is or the cable. And voids tend to be more irregular generally, or flatter between structural objects, depending on what's caused the void, obviously. So there are certain things we can do to try and work out what it is, but obviously if we've got more information in terms of like the as-built, so we know there's metalwork in the structure, we can then be looking out for that. If we know that it's going to be about 120 mil into the structure, then that's great, we can look out for that as well, and then we can use that to work out relatively where other features are and stuff like that. So hopefully that answers the question.
Yeah, and a follow-up to that, are you able to identify drainage pipes beneath the ground where there's reinforced concrete slabs?
It's definitely a lot more difficult, as I mentioned, with regards to masking signals. Reinforcement being metal is a massive reflector of ground penetrating radar energy. So it kind of depends on how close together the reinforcement bars are spaced, and also how deep the drainage is. So if it's quite deep drainage, if it's quite large, then yeah, if it's large, it might be able to be visible. If it's deep and small, a lot less likely, even without the reinforcement. If the reinforcement bars are just too tightly together, though, it's going to really reduce your penetration depth of your radar potentially to nothing, effectively. So it's not impossible, but it is a lot more difficult.
Right, okay. So are there other geophysical techniques you can use on the structure which will get similar results and the detail as the GPR?
Yeah, so the document that I highlighted earlier, the Environment Agency one, that discussed application on spillways, that's a really good reference for looking at these different techniques. So I would definitely advise, if you're looking for that, to have a read of that document. But we've got other techniques such as pulse impact echo, which is an acoustic technique. So it's similar to seismics, but on a really small scale. We've used that to look again for voiding within structures, because it's measuring changes in the elastic property, so how well a material will bounce back once it's been impacted, and obviously that's going to be different if that material's got a hole in it compared to when it doesn't. So
Okay, so a couple more questions here. Do you need to tie in, I think you covered this slightly, do you need to tie in the survey results to intrusive investigations to calibrate?
yes, I would say that's always preferable. Where we haven't, especially where we don't have an intrusive investigation, if we have coring, such as when we're looking at highway structures, for example, we can use that to understand how thick the different layers of the highway are, and then use that to calibrate our depths and better understand that variation within the GPR data then.
And does that help then in structures, say in walls and where we're looking for drainage, if you've got that?
Yeah, so anywhere that we've got intrusive investigation, it's always better to come back to the GPR data or whatever geophysics data following the intrusive investigation. So while you can use the initial geophysical investigation to target any intrusives, it's better to come back to the geophysics data to reassess following that intrusive investigation to see how that's going to adapt your interpretation, because in some cases it could potentially change it quite a lot. So it is always good practice to come back and do that.
Fantastic. We'll have one more question. How sensitive is the microgravity if you've got surrounding buildings or changes in level on your site?
Yeah, so things like buildings, which are effectively mass either side, they can cause problems, as can topographical changes. There are certain corrections we can make to remove the effect of that. Again, understanding of what's going on around us is really important in that sort of sense. It can affect it, but it's not a deal breaker. It is possible to do gravity surveys around buildings. The main problem is if you've got lots of people or traffic or sound noise that's going to vibrate your instrument, then potentially that could then create additional noise, which can cause, again, problems with the microgravity survey. So there's a few elements of careful design that would have to be taken into account for those sort of situations. Okay, so it's probably better on more open sites. It's better, but it's not necessary. It depends again on the size of the target as well. So it's all to do with how big the signal is from whatever feature you're looking for compared to whatever is causing noise. And as long as that signal is big enough, we can see it. Right, fantastic. Okay, so we'll end the questions there. Thank you very much to Charlotte for a brilliant talk again. Any further questions will be answered once Charlotte's had a chance to review these. So our next Down to Earth talk will be on Tuesday, the 15th of January, and we'll look at the design and validation of engineered fill material for enabling development. But please remember to complete the feedback following the presentation. And thank you again for attending today, and we'll see you all in January.